Hello everyone. So let's start the discussion on radius of curvature. So this is the first video on it. So followed by this video, there will be a vector form of it with respect to radial acceleration, and then there will be next one, which is like the problems related to it, and all physics sort of problems we are going to discuss. So basically, radius of curvature is defined in a way that, like for a curvature, for a small part, if you consider, so definitely there will be some radius. So it is supposed to be a part of a circle or an imaginary circle. So the radius of that particular imaginary circle is called radius of curvature. So I'm going to consider, look at this, there is a small part here. Okay, this is a small part. And I'm going to make a circle over here. So as you can see, this part is actually an integral part of that circle. So the radius of that circle is called radius of curvature of this at that particular point. So this is fundamentally the idea of radius of curvature, and not only in the case of trajectories or xy curves. So this is my so-called yx curve, but also in other cases like a string is hanging on a roof, or some rotational motion problems. In many cases, we have to talk about radius of curvature. So a couple of conceptual understanding you need here. So first we will do the mathematical point of view of it, and then we will be moving to the remaining part. Okay. So what if I want to find out the radius of curvature at this point? So what will be the scenario? So I can just look at this. At this point you can say this part is actually integral part of that circle. So that the radius of that circle, apparently the radius of this circle, that is called radius of curvature. So this is the idea of radius of curvature. Now by using calculus, how we are going to find out radius of curvature, let's see. Okay. So next, let's go to another one. Okay. So I'm going to consider another curve here. So I need a small part of it. Okay, at that point I'm going to find out the radius of curvature. Let me consider this circle, and as you can see, the small part, actually this part is being the part of, or it is an integral part of the circle. So as you can see, I would like to call it as dl. So this is my dl. And also, since it is on xy axis, I can also make this as dx, and this is dy. I hope that thing is clear. I don't think that is a big problem, right? Okay, now look at very clearly. This particular part is actually making some sort of angle, very small angle at the center, O. Let me call it as d theta. I would like to call it as d theta, a small angle. So what is the relation connecting dl, d theta, and the radius of the circle r? So I would like to call this is dl. Okay, this is a small arc dl. So we know that. So this is my so-called yx. Okay. So we know that dl is equal to r d theta, or in an easy way you can say arc is equal to radius into angle. So now what about r then from this? So I can write r is equal to dl divided by d theta. So this is what I want. See, this is what I'm going to use in order to make my radius of curvature equation. And I'm going to find out what is dl and what is d theta, and we are going to substitute over there. That's it. Okay, so let me get dl first. What about dl? We know that dl is equal to, from the triangle, it is very clear, it is root of dy square plus dx square. I'm going to do a small rearrangement here. That is, you take dx square outside, then it will be dy by dx, the whole square, plus 1 into dx. Okay, that why did I do this? You will understand later. Okay. Then this is my equation number 1. I call this as equation number 1. Now I'm going to move to the d theta part. So in order to get d theta, what I'm going to do is, let me just consider, look at the triangle again. So this is my dl, this is my dx, this is dy. So this is dy, dx, and this is dl. I would like to consider the theta angle here. So let's say, what is theta? How much would be theta? The theta would be dy upon dx. dy by dx, right? For small angles theta. This is apparently tan theta. So tan theta, the slope is dy by dx. Now you just differentiate this equation. You differentiate this equation, then it will be sec square theta d theta divided by dx is equal to d square y by dx square. So I differentiated with respect to x. So sec square theta into d theta by dx, like chain rule, is equal to d square y by dx square. What is sec square theta? That is 1 plus tan square theta into d theta divided by dx is equal to d square y by dx square. So that part has been sorted, right? Now already we know what is tan theta, that is dy by dx. So I can write 1 plus dy by dx, the square, into d theta divided by dx is equal to d square y by dx square. So I would like to make a small thing. I want only d theta. All remaining terms I am taking on the other side. So it will be d theta is equal to d square y by dx square into dx. This dx will come over there, divided by, look at this, divided by, what will be this term? That is 1 plus dy by dx, the whole square. That's it. Now what is our next thing? Yes, substitute in this equation. We already know r is equal to dl by d theta. So substitute over there. So radius of curvature r is equal to, what is my dl? I already know what is dl, right? Yes, dy, yes, root of dy by dx the whole square plus 1 into dx, all divided by, so this term, right, d square y by dx square dot dx, all divided by 1 plus dy by dx square. So basically this dx got cancelled. Okay, so you can see that this is also 1 plus, you can see this is also 1 plus dy by dx the whole square. This is also 1 plus dy by dx the whole square. So it will be, when it comes on the numerator, so it will be 1 plus 1 by 2 will be coming. So how much it would be? So I can write r is equal to, so 1 plus dy by dx the whole square, the whole raised to 1 plus 1 by 2, 3 by 2, divided by d square y by dx square. So this is fundamentally the equation for radius of curvature. So this is the equation for radius of curvature. The calculus equation is r is equal to 1 plus dy by dx the whole square, the whole raised to 3, the 1 plus dy by dx square, the whole raised to 3 by 2, divided by d square y by dx square. So based on d square y by dx square, the value of r could be positive or negative. If d square y by dx square at that point is negative, then r is negative. So I hope you can actually connect this with your maxima minima concept as well. Why? The numerator can't be negative. It will be always positive. So the first thing is that if d square y by dx square is positive, then r is positive. Okay. So if double derivative, second derivative is positive, what does that mean? Minima. So similarly, in the other case, d square y by dx square is less than 0, then r will be negative. So what does that mean? It is maxima. Okay. So local maxima, local minima concept, I hope you remember. So it's like, I'm not going in detail of that, but this is the idea. So we will discuss a little bit more about this in the next video. So let's see. Thank you.